One of our last topics in probability is called binomial expansion. And what it's doing is taking a binomial and raising it to different exponents or powers and quickly being able to expand instead of having to do all the distributions. So we'll do some expansions, we'll find the pattern, and then I'll show you a really quick and easy way to deal with this and not have to worry about a formula. So if we think about some binomial, x plus y raised to some exponent n, let's expand a few real basic ones, and these we should know. X plus y to the 0, any number to the 0 is 1. X plus y raised to the first, well, any number to the first stays the same, so that would be x plus y. X plus y squared, you know, is x plus y times x plus y. And when we double distribute that and clean it up, we get x squared plus 2xy plus y squared. 2xy comes from 1xy and 1xy, double distributing. At this point in algebra 2, you should be able to do that real quickly. For the next thing, we're going to use this answer to x plus y squared to expand x plus y cubed. Well, x plus y cubed will be x plus y squared times another x plus y. So we're going to take an x plus y and multiply it through x squared plus 2xy plus y squared, which is the result of x plus y squared. So again, x plus y cubed is equal to x plus y times x plus y squared. We're going to distribute x times x squared, x times 2xy, x times y squared. We're done distributing the x's, now we'll move to the y's. Y times x squared is x squared y, and it lines up with this x squared y. Y times 2xy is 2xy squared, which lines up with this xy squared term. And y times y is y cubed. When we clean it up, by combining like terms, we get x cubed plus 2x squared y plus 1x squared y is 3x squared y. 1xy squared plus 2xy squares is 3xy squares plus y cubed. So there are some things you need to notice. First of all, if you look at the exponents on your x for all of these, for x plus y all squared, x starts squared and goes down to x to the first, and then x to the 0, which is 1. We don't even write that. On x plus y cubed, we start with x cubed as my first term, and that exponent goes down to 2, then 1, then 0. So the powers of x start with the exponent and decrease by 1 for each term. Similarly, the powers of y, we don't have a y term, so it's y to the 0, and it goes up by 1 each time. Y to the first and ends at y squared on the x plus y squared expansion. On the x plus y cubed expansion, there's a y to the 0, y to the first, y squared, y cubed. So the x's start with the exponent and decrease by 1. The y's start with y to the 0 and increase by 1 for each term. That pattern holds true always with an expansion of the binomial. If you look at the sum of the powers or exponents of any term, like here, this exponent is 2 plus 1 is 3. It's the same as the exponent on the problem. This exponent is 1 plus 2 is 3. Same as the exponent on the problem. These exponents, 1 plus 1, add up to 2. Just a 2, just a 2. So the sum of the powers is equal to the exponent on the binomial. So what we could do is use the formula that's given in this box, which gives a general pattern for a binomial expansion, x plus y to the n. It starts with a combination, which gives us the leading coefficients, nc0 times x, the first term raised to the exponent on it, like here, x cubed, plus nc1, that gives us the coefficient, times x to the n minus 1, the exponent on x is going down by 1 each time, times y to the first, plus nc2, the exponent's gone down 2, we're on our next term, the exponent on y has gone up 1, and so on. You could memorize that formula if you wanted to. You don't have to memorize the formula because it is given to you on your Regents reference sheet. Here, there's your binomial expansion theorem, they call it, and they use A's and B's instead of X's and Y's. This is it using summation notation, same thing. Or what we could do, which I find much easier and most of my students find much easier, is use Pascal's triangle. But if we look at Pascal's triangle, this gives us a lot of things that we discovered in class today, but it also will give us the coefficients, I spelled that wrong, on the terms in a binomial expansion. Okay, so here's how that works. If we think about what we got when we did x plus y to the 0th exponent, all we got was a 1. So the first row in Pascal's triangle is the expansion to the 0. If we look at the coefficients on the expansion x plus y to the first, it's really 1x plus 1y. There's the second row in Pascal's triangle. So these are the coefficients on a binomial expansion to the first. If we look at the coefficients on x plus y squared, there's really 1, 2, and 1, which is fourth row of Pascal's triangle, 1, 2, 1. So the long expansion we did should have the coefficients 1, 3, 3, 1. And sure enough, it does. 1, 3, 3, 1. So I prefer to use that pattern from Pascal's triangle and the pattern of knowing that the exponents on x go down by 1 each time and the exponents on y go up by 1 each time to do an expansion more quickly. So if we come to the bottom and we want to expand x plus y to the 4th, exercise 2 part A. Well, the first thing I'm going to do is go to Pascal's triangle and get my coefficients. This is the 0th, 1th, 2nd, 3rd. So these are the coefficients on the 4th expansion, the binomial expansion to the 4th. So I need 1, 4, 6, 4, 1 as my leading coefficients. I write those down with lots of space in between. 1, 4, 6, 4, 1. And then I know my pattern on my variables. X starts with the exponent on the problem, here 4, and goes down by 1 each time. You can write it out if you want, and then clean it up later. Y, I start with no y, so it's y to the 0, and it goes up by 1 each time. All of your exponents should add up on each term to the 4 on the problem. And then you can clean it up. We don't write the 1 or the y to the 0, which is also 1. We just write x to the 4th. Here we would write 4x cubed y, 6x squared y squared, 4xy cubed, and we don't bother with these ones, and we end with y to the 4th. So understanding the pattern, being able to create Pascal's triangle, will save you a ton of time in doing these expansions. Let's do x plus y to the 5th. Find the 5th row, remembering to count the first one you see as the 0th row on Pascal's triangle. So here's the 0th row, 1, 2, 3, 4, 5. Some people also see that 5 is the second term, which tells us the row we need. So my coefficients will be 1, 5, 10, 10, 5, 1. So the coefficients on this expansion are 1, 5, 10, 10, 5, and 1. The pattern with my variables and the exponents, x starts with the 5th and goes down by 1 each time. Y starts to the 0 and goes up by 1 each time. And then you clean it up. So in my world, I don't need that crazy looking formula on this note sheet or on your Regents reference sheet. I know that math is all about patterns. It is consistent. And I use that knowledge to save me some time and aggravation. Now, binomial expansion can be a little bit more challenging when the binomials aren't simple. So let's expand 2x minus 1 to the 4th. We're going to write it in standard form and simplify it. Well, math is consistent, so I'm still going to look at that exponent on my problem and go to that row in Pascal's triangle for leading coefficients. So I need 1, 4, 6, 4, 1. Give myself lots of space. I still take my first term, but here it's 2x, and I raise the whole thing to the 4th, and then it goes down, the exponent on it goes down by 1 each time. And then I still take my last term, negative 1, and I raise it first to the 0, and then its exponent goes up by 1 each time. And now you clean it up. You just need to be a little more careful. 2x all to the 4th is 2 to the 4th times x to the 4th. Well, 2 to the 4th is 16. X to the 4th, these are still 1s. Here I have 4 times 2x cubed. Well, 2 cubed is 8. X cubed, and that's times 4. And I have negative 1 to the 1st, so this is all times negative 1. So cleaning up, my first term will be 16x to the 4th. My second term is 4 times 8 times negative 1, which is negative 32x cubed. Now for my next term, I have 6 times 2x all squared, which is 4x squared, times negative 1 squared, which is positive 1. Cleaning it up, 6 times 4 times 1 is positive 24, and I have x squared. My next term, I have 2x to the 1st, which is 2x, times 4, times negative 1 cubed is negative 1. 4 times 2 times negative 1 is negative 8, and I still have that x. And for my last term, I have 1 times 2x all to the 0, which is also 1, times negative 1 to the 4th, which is positive 1. So the pattern is the same, but you just need to be more careful, and you raise whatever your first term is to the exponent on the problem, going down by 1 each time, and whatever your last term is, starting at a 0 exponent, going up by 1 each time. Sometimes you have negatives, and you have to be super careful raising negatives to exponents.